Good morning, my name is Liu Yutao and I am pursuing my master's degree at University of Chinese Academy of Sciences. Today I'll introduce our new work, NeUDF, Learning Neural Unsigned Distance Fields with Volume Rendering. Given a few multi-view images, our goal is to reconstruct the shapes with arbitrary topologies. A previous work, NeUDF, leverages SDF to model closed shapes, and achieves impressive reconstruction results. However, SDF cannot represent shapes with open surfaces. In our work, we use UDF to model shapes with arbitrary topologies, and propose a UDF-based volume rendering framework in a NeUDF-like paradigm for network optimization. Our method can reconstruct both open surfaces, like the plant leaves in the up row, and closed shapes, like the fruits in the bottom row, solely from multi-view images. For the 3D reconstruction task, classical approach requires 3D scanning to get dense point clouds, and manually processing to convert the point clouds into meshes, which is expensive and requires expertise. Recently, the processing of neural radiance fields has greatly improved the multi-view image reconstruction. With a few phone-captured pictures, the network can optimize a NeUDF by network optimization, which is efficient, low-cost, and user-friendly. For an object to reconstruct, NeUDF learns the mapping from the spatial position and view direction to color and density at the sample point through volume rendering. There are several works using NeUDF-like methods for 3D reconstruction of closed shapes. They leverage SDF as surface representation, which adopts strong assumption of watertight shapes, limiting the reconstruction of complex shapes with open structures. To overcome this limitation, we propose NeUDF, a UDF-based volume rendering framework for 3D reconstruction of both closed and open surfaces. In our work, we propose to use UDF as the surface representation. We observe that, instead of learning a criterion to divide the space, which may get stuck in local maximum due to the closed surface prior of SDF, the optimization of UDF is to learn local minimal values, which is flexible in topology. Different from SDF, UDF adopts no explicit surface constraint which causes ambiguity locating the surfaces. As shown in the picture, one can easily distinguish whether the ray intersects the surfaces in SDF. But in UDF, the graphs are quite similar, making it difficult to test whether there is really an intersection or the ray just passes by the surface edge. Furthermore, when the network is not fully converged, there is also inevitable perturbation near the zero point of UDF network, making the intersection detection even more ambiguous. We propose a dedicated weight function in volume rendering to address this issue. The weight function bridges the image color in UDF. Similar to SDF, we want the weight to be unbiased and occlusion aware for UDF, and further to be aware of the ambiguous surface detection of UDF. The weight function is structured as WR. Any function satisfying above rules is compatible with our framework. We experimentally choose one function and get a simpler formulation as below. Next we will illustrate the performance of the weight function in several typical cases. The weight function WR involves two trainable parts, the UDF value, psi, and the scale parameter value, r. In the simplest case, where there is only one intersection, we show the weight function graph with changing UDF and changing r, respectively. It can be seen that the weight is unbiased. In case 2, there are two intersections along one ray. It can be seen that the weight is occlusion aware in a dynamic manner, despite the ambiguity of UDF zero-point detection. In case 3, there is one intersection and one passing by surface, which is a typical ambiguity for open surfaces. With small r, the function acts like NeUDF and is tolerant to small perturbation. With increasing r, the function is less tolerant, forcing the zero point to be accurate. By simultaneously optimizing UDF and r, the edge of surface can be distinguished, avoiding local maximum. See the narrow crack between two nearing edges of the rack model. We further show the comparison with a naive solution in multiple intersection cases. The naive solution is to directly use the same weight structure of NeUDF, WNeUDF. From the picture it can be seen that, even given the precise UDF value, the naive solution still distributes non-zero value at every intersection point. This means the rendered color is constantly a mixture of visible and invisible surfaces, preventing the network from learning the real color of single surface or distinguishing each surface. The network compensates for this bias with spurious surfaces. See the noise and poorly distinguished edges of the bull model. In contrast, our function is aware of the surface invisibility and free from inner noises. Besides, we use upsampling and regularization for better optimization. We separate the sampling weight and rendering weight in training. The rendering weight is accurate and sharp at the intersection point. The sampling weight is smooth and balanced, within an interval near the intersection points. The usage of two separated weight functions stabilize the network optimization, especially in occluded regions. We use the normal regularization to enhance the gradient consistency. The ambiguous normal at the surface point is replaced by the interpolation of nearby normals. The normal regularization benefits network optimization in cases with picture ambiguity. We visualize our results of real captured and complex synthetic data. It can be seen that the reconstructed open structures are with high fidelity. We also visualize our results of synthetic, garment, real captured, D2 and BMVS datasets in dynamic pictures. We show the comparison with previous works on open surfaces. Ours achieve both accurate geometry and topology. We tested multiple weight functions satisfying our rules, all of which is capable of UDF-based reconstruction. We experimentally choose the one that converges fastest. We also tested other key components of our method. Qualitative and quantitative experiments show that our key components are beneficial for the reconstruction. Our method has some limitations. For cases with poor visible information, for example heavy occlusion or lack of varied view directions, the mesh cannot be well reconstructed by our method. For high-frequency details, UDF faces difficulty in optimization and mesh extraction without explicit surface constraint. On the other hand, a future research direction orthogonal to our method is the meshing tool. Existing meshing tools specialized for UDF are not as robust as marching cubes for SDF. For example, the mesh extracted by Mesh UDF sometimes contains periodical ripples. Extracting normal consistent and fine detailed open meshes from UDF by modifying classical approaches for meshing closed surfaces, such as sampling a point cloud and running screened Poisson, is time-consuming and requires expertise. Thanks for your attention.